Pause this video for a second and read this excerpt from page 288 about connecting semester 1 and semester 2 of calculus, so differential calculus and integral calculus. So here's the beginning of that connection between integral and differential calculus. You can evaluate a definite integral. I mean, get an exact answer, not an approximation because you used the right number of rectangles and you used enough rectangles that your estimate was good enough. But you can get an exact answer if you can find an antiderivative for the integrand. So remember, the integrand is the function inside the integral. So for this integral here, the integral from a to b of f of x dx, the integrand is f of x. If I can find any antiderivative of f of x, we know how to take derivatives. So to find an antiderivative, we just have to sort of run through the catalog in our head and see if we can think of a function whose derivative would be f of x. But if we can find one, then all we have to do is evaluate that antiderivative at the upper limit and subtract what we get when we evaluate that antiderivative at the lower limit. So let's try these examples. I want to find the area under the sine curve from 0 to pi. So my first step is to think of a function whose derivative is sine. That process, thinking of a function whose derivative is a certain function that you already know, is called finding an antiderivative. We're going to have lots and lots and lots of rules for finding antiderivatives. Right now, what we want to do is just sort of run through the list of functions that we can take a derivative of and see if the answer to any of those questions is sine of x. So we might think, we know sine and cosine are related when we take their derivatives. The derivative of cosine is negative sine. So here, if I'm looking for an antiderivative for sine, I'm going to say my antiderivative, which I'm just going to come over here and call capital F of x. F of x, capital F, can't be cosine, because derivative of cosine is negative sine. Capital F is negative cosine of x. And that's just me sort of in my head taking the derivative of a bunch of functions until I find one whose derivative is sine. So here's the notation I use. I think of that capital F of x equals negative cosine of x as something I just wrote over on the side, sort of as my thought process as I do this problem. So that integral is equivalent to the antiderivative of sine of x, which is negative cosine of x, evaluated from 0 to pi, from a to b. And a notation I use, I'm going to write down my antiderivative. I use this vertical line to say I'm going to evaluate it from, I'm going to copy these limits. That's 0 to pi. Those are the a and the b in my original integral. So now what I'm essentially computing is negative cosine of pi minus negative cosine of 0. F of b minus f of a, where b in this case is pi, the upper limit, a is 0, the lower limit, and capital F of x is negative cosine of x, because negative cosine of x is an antiderivative of sine of x. So now to evaluate this is negative cosine of pi, so I could write this out, negative cosine of pi minus negative cosine of 0. So that's capital F of b minus capital F of a. This is a very common error to not put parentheses around that second function and make sure the subtraction gets distributed. So the cosine of pi is negative 1. So the negative cosine of pi is negative negative 1, which is positive 1. I have a minus here. I have the opposite of cosine of 0, so that's going to be minus. Cosine of 0 is 1. So I end up with 1 minus negative 1, which is equal to 2. For example 2, I'm going to need to think of an antiderivative of secant squared of x. So can I think of a function whose derivative is secant squared? So you definitely want to get to the place where you can do this, where you just sort of have a catalog in your head. So hopefully you thought of our friend tangent of x. So I'm just over here, you wouldn't necessarily write this as part of your work, but I want you to understand my thought process. I'm looking for an antiderivative of secant squared of x. I know that that function I'm looking for is tangent of x. So what I'm going to write is that my original integral is equal to, the antiderivative of secant squared is tangent, so it's going to be tangent x, evaluated from 0 to pi over 4, and that's equal to the tangent of pi over 4 minus the tangent of 0. That's equal to 1 minus 0. My final answer here is 1. Before we do this last example, it's just a released problem from the multiple choice test. We want to remember how we found derivatives of polynomial functions, because that process is going to help us to think about how we could find an antiderivative of a polynomial function. So I'm just going to make something up. I'm not even going to call it f. I'm going to call it g. G of x is 5x to the 6th plus 7x cubed. How do I find the derivative? I just totally made that problem up just to help us remember what we used to know. To find that derivative, I'm going to take the old exponent 6 multiplied by the 5 that was there. So 6 times 5 is 30. My new exponent is going to be 1 less than the old exponent, so I'm going to have 30x to the 5th. Plus the 3 will multiply by the 7, 21x squared. So step 1 was multiply by old exponent, and step 2 was reduce exponent by 1. So if I want to undo that, and antiderivatives are undoing of derivatives, I have to reverse that process. So to find an antiderivative of a polynomial function, for each term in the function, I'm going to increase the exponent by 1. I'm undoing these steps in backwards order. I'm going to increase the exponent by 1 and divide by that new exponent, because increasing by 1 undoes reducing by 1, and dividing undoes multiplication. So increase the exponent by 1 and divide by the new exponent. So here's this problem. So to evaluate this definite integral, I'm going to need an antiderivative of 4x cubed minus 6x. So I'm going to start by finding the antiderivative of 4x cubed. I'm going to increase the exponent by 1. So my antiderivative, which I'll just call capital F. I'm going to increase the exponent by 1, so I'm going to have x to the 4th. I already have this 4 out here multiplying, and I'm going to divide by the new exponent. So the new exponent is 4. I'm going to have a subtraction sign. I have a 6x. I'm going to increase the exponent by 1, so that is 6x to the 1st. It's going to become 6x squared. And I'm going to divide by the new exponent. So the antiderivative function that I'm going to use is x to the 4th minus 3x squared. How could you check your work? Check your work by taking the derivative of x to the 4th minus 3x squared, 4x cubed minus 6x, and just double check that you get this integrand that you're starting with. So I'm going to write that up here. I'm going to use f of x equals x to the 4th minus 3x squared. And here's what I'd do. I'd say the antiderivative of, well, the integral from 1 to 2 of 4x cubed minus 6x dx is going to equal, my antiderivative is x to the 4th minus 3x squared, evaluated from 1 to 2. So that's going to be, I'm going to come through and I'm going to plug in 2 for all the x's. So it's going to be 2 to the 4th minus 3 times 2 squared. And I'm going to subtract. Here's where you have to be really careful. You have to use some kind of grouping symbol after the subtraction. You're going to have that same problem we've seen all semester long where the subtraction won't get distributed. And you'll end up with the wrong answer. So after the subtraction sign is supposed to come what I get when I plug 1 into the capital F function. So that's going to be 1 to the 4th minus 3 times 1 squared. And you can simplify this on whatever order works for you. That's going to be 16 minus 12 minus the quantity 1 minus 3. So 16 minus 12 is 4 minus negative 2. It's a final answer of 6. So Our answer is C.